Hello everyone. Today I will present our work titled, Advancing Quantum Workforce Development Through Hands-on Education in Circuit Design, Optimization, QML, and Security. This work focuses on how we can prepare students for the emerging quantum workforce by moving beyond theory-only instruction and building a practical, design-centered learning pathway. The presentation is framed around a modular educational approach that connects quantum computing, microelectronics, machine learning, and hardware security. Quantum technologies are rapidly evolving, and they are increasingly connected with artificial intelligence and hardware security. However, bringing quantum topics into STEM education is still challenging. Students often face high conceptual complexity because many quantum ideas are abstract and physics-heavy. Existing programs can also be isolated, with curricula that focus heavily on mathematics while remaining disconnected from broader AI and engineering ecosystems. To prepare students effectively, we argue that education should include design-centered and interactive lab experiences, where students learn by building, analyzing, and testing quantum systems. This slide highlights the educational imperative behind the proposed framework. The goal is to bridge the gap between theoretical quantum concepts and practical microelectronics education. The figure shows students from many disciplines entering the learning pipeline, including engineering, science, IT, business, economics, and other fields. The middle of the slide represents the challenge: advanced physical principles, complex mathematical models, and uncertainty can create barriers. Our proposed modular workshop framework acts as a bridge, helping students move from initial exposure toward participation in the quantum workforce. Here we introduce the unified educational architecture as a quantum computing workforce pipeline. The framework is organized around a design-centered progression. In the first phase, students learn foundations and building blocks, including quantum fundamentals, Dirac notation, reversible logic, and Clifford plus T gates. In the second phase, they move into quantum arithmetic engineering, where they compare exact adders, optimize resources, and reason about fault-tolerant design. In the third phase, they explore advanced security and resilient system design. The destination is a set of possible career and research paths, including quantum hardware design, quantum algorithm research, and quantum cybersecurity. This slide summarizes the structure of the proposed educational architecture. Instead of offering isolated lectures, we propose a comprehensive pipeline with 3 learning phases and 6 integrated modules. The key shift is from syntax-driven programming towards system-level architectural reasoning. Students first learn how to build circuits, but then move toward deeper questions such as architecture-level trade-offs, noise interpretation, and approximate design. This progression is important because practical quantum computing requires students to understand not only how to write code, but also how design choices affect performance, reliability, and security. The instructional pathway is organized into 3 phases. Phase 1 focuses on foundations, where students establish the basic building blocks of quantum computing. This includes quantum fundamentals, Dirac notation, reversible logic, and Clifford plus T gates. Phase 2 focuses on arithmetic, where students engineer robust quantum systems and compare ripple carry adders with carry-Lucas head adders. This phase also introduces resource optimization and the dominance of fault-tolerant design. Phase 3 focuses on security and careers, preparing students to think about resilient system design and possible career paths as quantum hardware designers, algorithm researchers, and cybersecurity specialists. This slide connects lecture components with their learning focus. Linear algebra, state representation, and unitary transformations establish the formal basis for quantum computation. Concepts such as superposition, entanglement, measurement, and state evolution help students develop intuition about quantum behavior. Reversible computation and quantum adders introduce students to circuit design and fault-tolerant considerations. Other topics such as circuit depth, ancilla usage, peephole optimization, TAGs, and topology-aware partitioning help students understand trade-offs, scalability, connectivity, and decomposition. Finally, data path design, machine learning concepts, hybrid workflows, and security connect quantum systems to classical pipelines and secure design. The first 2 laboratory modules provide the hands-on foundation of the framework. Module 1 focuses on Qiskit foundations. Students design and run basic quantum circuits, learn gates, superposition, and entanglement, and gain direct experience using quantum software tools. Module 2 focuses on noise-aware quantum adders. In this module, students study quantum arithmetic from both logic and circuit design perspectives. They compare exact and approximate adders and analyze performance under noise and hardware constraints. Together, these modules help students move from basic circuit construction to realistic evaluation. The next 2 laboratory modules build on that foundation. Module 3 focuses on adder architecture analysis. Students compare ripple carry and carry look-ahead adders, study the trade-off between circuit depth and ancilla usage, and examine reversible computing and cleanup operations. Module 4 focuses on quantum security. Here, students study security challenges in NASQ systems, including noise-induced and platform-level vulnerabilities. They also perform hands-on attack analysis using quantum adders. This connects circuit design directly with security reasoning, which is essential for future quantum systems. The final 2 laboratory modules extend the framework toward projects and hybrid workflows. Module 5 is a capstone project where students design exact and approximate quantum adders, evaluate accuracy and noise robustness, and analyze security vulnerabilities in Trojan attacks. Module 6 bridges classical machine learning to quantum machine learning. This module helps students connect familiar machine learning workflows with quantum analogs and develop intuition for hybrid quantum classical pipelines. These modules are intended to show students how quantum methods can fit into broader emerging applications. Assessment is built into the framework through multiple evaluation strategies. Formal assessment is implemented through code completion tasks, circuit analysis, and interpretation of measurement outcomes. These activities support hypothesis testing and help students connect implementation with reasoning. A multidimensional rubric evaluates implementation accuracy, conceptual understanding, architectural trade-off analysis, and clear communication. Finally, capstone delivery requires students to compile their implementation results and defend their architectural analysis under realistic noise and security constraints. This ensures that students are assessed not only on whether their code runs, but also on whether they understand the design implications. The expected student learning outcomes reflect the full design-centered scope of the course or workshop sequence. Students should be able to explain how quantum computing affects system design, optimization, and security assumptions. They should design and analyze quantum circuits using metrics such as depth, ancilla usage, and gate complexity. They should implement and evaluate quantum arithmetic structures, apply approximation and optimization, use quantum software tools for simulation and benchmarking, and integrate security-aware thinking into quantum circuit design. Just as importantly, they should be able to communicate design trade-offs and experimental results clearly and reproducibly. Looking forward, this framework can support broader workforce development in several ways. First, hands-on QML modules can be expanded and connected to execution on real quantum hardware. Second, tiered project tracks can be developed for diverse learner groups, allowing students with different backgrounds to participate meaningfully. Third, formal educational evaluation through pre- and post-assessments can provide empirical evidence of learning gains. Finally, extending the framework toward quantum design automation workflows, including mapping, partitioning, and approximate synthesis, can align instructional activities with real-world quantum toolchains. The pedagogical philosophy behind this work is that effective learning often requires more than gradually expanding traditional models. In quantum education, students may need a fundamental conceptual shift. They must move from seeing quantum computing as only equations or isolated programming tasks toward understanding it as a system design problem. By combining foundations, hands-on labs, optimization, security, and hybrid workflows, the proposed framework aims to support that shift. Thank you for your time and attention. I would be happy to take any questions.